Hey folks, we're going to use Gauss's law to calculate the electric field created by spherically symmetrical charges. And I got two examples, okay? So the first example is imagine that I have a hollow ball, like a plastic ball, and the total charge on that plastic ball is Q. It is hollow, okay? And we're going to calculate the electric field outside and then inside of that hollow plastic ball with a charge Q on it. So we're going to use Gauss's law. So we have our double integral closed surface of E dot dA equals Q in over epsilon naught. Well, we'll call this outside location A and the inside location B. Well, look at location A. Um, I'm going to have, it's a positive charge, assuming it's a positive charge. The surface I'm going to draw is going to be concentric with the sphere. And then it just becomes E times A, which is 4 pi radius squared. Okay, that's the surface area of that blue sphere that I drew around my solid or my hollow sphere. And how much charge did I get inside that blue sphere? Well, I got all of it. So it's just Q over epsilon naught. And so your electric field ends up being Q over 4 pi epsilon naught r squared. Knowing that K is 1 over 4 pi epsilon naught, you get E equals KQ over r squared. And lo and behold, that's the same thing as a point charge. So whether you have a hollow ball of charge or a point charge, if you are outside of it, the electric field looks the same. Okay, so the electric field would kind of, if I'm outside of this, the electric field would look like this. Okay, just like a point charge looks like. All right. Now, what if we are inside? So this would be outside. All right. Well, what if we're inside? Okay, so inside the ball of charge. Okay, so let's say you're at location there, location B. Well, I'm going to draw a concentric sphere with the hollow ball of charge. Okay, centered at the same spot. And I'm going to use the same surface, so it's 4 pi r squared, it's a sphere. But this time, what's Q? How much charge is inside that red sphere? So you get E times 4 pi r squared equals, well, how much charge is inside that red sphere? None, okay, over epsilon naught. So E on the inside would be 0. And therefore, like if you're inside that sphere, you would feel there'd be no electric field in there at all. If I were to graph for this whole thing, the magnitude of the electric field versus R, the radius of the sphere, I'll call that capital R, that's a point of interest. If you're outside of this, it's going to be an inverse square, that's your KQ over R squared. If you're inside of it, as you drilled through the shell, your field would drop to 0. And then if you're inside the sphere, your electric field would be 0. So that's what you'd have if you had a hollow sphere with all the charge on the surface. Okay. Well, what if instead of that, what if we had a solid ball of charge? Okay. So imagine I had a plastic ball that was solid and it was uniformly distributed charge throughout the ball. So inside and out, the total charge is Q, the radius of the ball is R. Okay. What would the electric field look like if you're inside and outside of that ball? Okay. Well, if you're outside the ball, okay, so we're going to draw our Gaussian surface outside the ball, concentric with the ball. Okay. And you do your double integral E dot dA equals Q in over epsilon naught. Well, again, we picked a surface such that E is perpendicular to A at all points and the same strength at all points. So you end up with E times 4 pi r squared equals, well, how much of the total charge is inside that blue sphere? Well, all of it. So you get the same answer we got before. If you say that K is equal to 1 over 4 pi epsilon naught, you get E equals KQ over r squared. So it looks the same as a point charge. It's the same as the last example and the same as the previous video with a point charge. Now here's where the difference lies. What if you start to drill inside this ball of charge? Okay, so let's say you are right there. Okay, what's the electric field strength there? Well, here I'm going to draw a concentric sphere with the ball of charge. That includes the point I'm interested in. And the left side of our equation is going to be exactly the same. You have E times the surface area of that red sphere would be 4 pi r squared. The difference is going to be what on earth is Q in? Okay, I have not captured all the charge of that black sphere. I've captured some portion of it, right? How much charge is inside that red sphere that I've drawn? Well, there's a couple ways to do this. One simple way is to say the following. The charge that I capture, I'm going to call that Qn, over the total charge of that black sphere is proportional to the volumes, okay, of the spheres. So this would be, what's the volume of a sphere? Well, it's 4/3 pi r cubed over 4/3 pi big R cubed. Okay, now remember, big R is the radius of the sphere. That's a constant. It's not going to change. The 4/3 drop out. And so if you write Q in here, in terms of the other stuff, you get the charge that I captured is equal to the total charge that I had originally times the ratio of the radii cubed. This is what we're going to plug in for Q in. Okay, so we get E times 4 pi r squared equals big Q, the total charge of the black sphere, times the ratio of the radii cubed divided by epsilon naught. And then if you do your algebra here, this r squared will cancel with that r squared, leaving you, sorry about that, leaving you with an r. And you get the following. You get E equals Q times R over 4 pi epsilon naught big R cubed. Okay. And if you write that in terms of K, remembering that K is 1 over 4 pi epsilon naught, you get KQR over big R cubed. So that's our electric field inside the sphere. Now let's talk about that just for 1 second. What kind of math function is this? Remembering that the total charge Q of the sphere and the radius of the sphere are a constant. These are each constants. What's the thing on the right side that varies? Little r. Okay, so what kind of equation do we have? We have a linear function. Everything in front of the little r is a constant. K is a constant, big Q is the total charge of the sphere, and r is the radius of the sphere. Those things don't change. But little r is a variable. Notice that the electric field strength, because it's linear, it's stronger when you're pretty far away from the center. But when you get to the exact center of the sphere, the electric field is 0. So at this spot where this little star is drawn, the electric field is 0, which kind of makes sense because every part of the sphere would make a field pointing toward you and they would all cancel. Now, trying to draw this would be rather difficult. So on the outside of this thing, we'd have an inverse square field like so. Okay, like that. And then how would we draw on the inside? Well, you'd have no lines to dead center. As you got farther from the center, okay, you'd have more lines. So it kind of would look something like this, maybe, okay? And as you got farther from the center, you'd have more lines, and then they would meet up with these lines here. If we graphed all this, okay, and this is where it gets interesting. So we have the electric field strength versus radius. The radius of the black sphere is a point of interest. When you're outside of this, your equation is KQ over R squared. When you're inside, you have a linear equation that is KQ little r over big R cubed. Notice that these match up at the surface of our sphere. If you put in for little r, if you put in big R, this equation and this equation will say the same thing. They'll both say KQ over big R squared. So that's your max electric field, KQ over big R squared. Okay. So when we're doing Gauss's law and you're trying to find Q in, if you can set it up as a ratio of the volumes. The charge that you capture is a ratio of the volumes. That's usually the most convenient thing to do. So you figure out, well, what's Q in, and then you plug it in over here, and you get your electric field inside of there. Now, there will be cases when the charge is inside the ball is not uniformly distributed, in which case you got to do a little more than this. But for now, we'll stick with this. I hope that equation for that video was helpful, and thank you very much.